Welcome to the second part of Lecture 7 of our second semester class on stochastic processes. We are still dealing with the Bismuth derivative formula for the derivative of the semigroup that is induced from solutions of stochastic differential equations. And we wanted to discuss this Bismuth derivative formula in the simplified case when we are dealing with one-dimensional stochastic differential equations which have a constant diffusivity matrix sigma equals identity, so which depend only or which differ from a standard Brownian motion only through the inclusion of an additional drift vector field B. And here in the previous lecture we established the following result, which reads as follows. So let B a smooth vector field, which in this case is sufficient to be of C1 regularity, and let us consider the solution to the stochastic differential equation, which is given through this B as a drift vector field and an additional additive, as we say, Brownian component, so the usual stochastic differential equation. And let us furthermore take a function phi, which is smooth enough, in our case, differentiable once in time and twice in space, and let us assume that this function is a solution to the following one-dimensional parabolic PDE, namely the time derivative of phi equals b times the derivative of phi, first spatial derivative of phi, plus a half second order derivative of phi. Then the following representation for the derivative, the spatial derivative of this function holds true, namely it can be represented as a certain expectation, which involves the trajectories of the process, plus a stochastic integral with respect to the input signal, the Brownian motion signal, which involves the product of two additional stochastic processes. Well, in one case, a stochastic process Q and a deterministic function L, which depends on time, which are supposed to be given in the Q case, in the case of the Q function, as solution to an ordinary differential equation with random data. Namely, we want that Qt is a little misprint. We want that Qt solves the ordinary differential equation that Q dot t equals Q of t times b prime at the location of the trajectory, the Q function starts in the position 1. So that's the one component, is the solution to this ordinary differential equation with random coefficients. And furthermore, L, this additional function which depends on time L, here is any function which is smooth in time, so it's just once differentiable, and we want to require that at initial time this L function is 1, and at terminal time, where t is a fixed time at which we want to give this representation, we want that this L function at this time where the representation is considered vanishes. So if we plug in this product of these two components, of the L component and the Q component, and use that product as the integrand against which is then integrated against the trajectories of the driving Brownian motion, and we take this stochastic integral up to time t, that's one of the two components which appear in this representation of the derivative, and the other component which is appearing in this derivative formula is this phi function which was appearing in the assumption of the theorem. So the Bismuth derivative formula in this case says if we have a smooth solution to this particular parabolic PDE, which is, as we already know, associated to this solution to the stochastic differential equation, or to the generator, effectively, of this Markov process which comes with the stochastic differential equation. If you have a solution to this parabolic PDE, then we can represent the derivative, the spatial derivative of this solution, as a certain functional which involves only the initial value or the initial datum of this parabolic PDE, which is then evaluated at the time at which we want to represent the spatial derivative of that phi function, times a certain stochastic integral which involves additional information about the data of this parabolic PDE. And the aim of this supplementary piece in this lecture is to use this information or this formula in order to give actually the similar or basically the same representation for the action of the semigroup. Note that in this formulation we are not yet there where we want to be, because the semigroup does not appear in an explicit form. And this supplement here today will be dedicated to passing this kind of representation to the case of the semigroup, which will be somehow an argument which involves a little bit of regularization. For that aim, let us start with a function to which we want to apply the semigroup. So we still want to connect with our theory of Feller semigroups and so forth. So ultimately we want to apply our semigroup, which is generated by the solution to the stochastic differential equation, to an arbitrary function f, which is in this function space that we typically work with when we're doing Feller semigroup theory. So we take a function f, which is continuous and vanishes at infinity, and it is important, or it will be important, to consider the case when the function f is actually smooth. And in order to guarantee this, we apply first a certain smoothing operation to that function. Namely, we can do this by simply modifying this given function f with a modifying function, with a standard Friedrichs modifier or something. And one way to do that is to use the standard Gaussian heat kernel, which is a standard tool also in analysis theory. If you want to have a function which is really smooth and you start from an arbitrary function, you just take this convolution with the Gaussian heat kernel, which produces a smooth function. So in other words, f epsilon of x is then just the convolution of the f function of the initial function convolved with the Gaussian heat kernel. The fact that the Gaussian heat kernel here is also the transition semigroup for the binding motion does not play any role. The only thing that plays a role is the fact that this produces a perturbation of the function f, which then will be smoothed to an arbitrary degree in space. Now, in particular, this function, if we started from a function which vanishes at infinity, all derivatives of that function will also vanish, the smoothened function will also vanish at infinity. And in particular, this smoothened function will be in the domain of the generator of our SDE, because we already know that C2 functions which vanish at infinity are in the domain of this operator, in the generator. And in this case, we have an explicit representation of the generator in terms of this PD operator, which is also the PD operator that governs this parabolic PDE, which was appearing in the previous result. In particular, we know that, so not only in particular, but since the function f is in our domain of the generator, in particular we know that the PT operation onto that function maps back into the domain of the generator. And from our abstract theory, we know that if we take the derivative of this semigroup action on the function, then we can write that as PT applied to the application of the generator to the function f epsilon. That's just general theory. We proved that some sessions ago. And since we know, as I said before, that the function f has this smoothness, we also have that the operator A acting on f epsilon has this concrete representation as this differential operator, curly L. And we want to convince ourselves now of an auxiliary claim, which we actually have to use, or which we have to make sure for the connection to the previous argument, that this function, that PT of f epsilon, that this function as a function in space is of C2 regularity. This will help us in the next step to actually map our previous result, which was for certain parabolic solutions, into the case that we're dealing with here with this function. So let us convince ourselves, as an auxiliary step, that this function has exactly, or has at least, this C2 smoothness with respect to the spatial variable. In order to convince ourselves that this PT operation applied to the function f produces or f epsilon produces a function which is C2 smooth, we will convince ourselves first that the solutions of our stochastic differential equations are differentiable with respect to the starting point. To that aim, let us consider the same stochastic differential equation as before, but now with a different starting point, namely y. This stochastic differential equation, or the solution to that, satisfies a corresponding integral equation, which is just equivalent to saying that it's in solution. And if we subtract the two corresponding integral equations for the two solutions starting in x and y, we obtain the difference of the starting points on the right-hand side. We get the difference of the ODE parts, or the integrals with respect to the time parameter, which entail the evaluations of these the B vector field on the trajectories of the respective two solutions. And we get the difference of the two Brownian motions, which of course produces cancellation, such that we end up with this representation for the difference of the two solutions. And we can divide this inequality simply by the difference of x and y. And since the vector field B is smooth with respect to the spatial position, we can deduce from this representation that in fact the derivative of this solution map with respect to the initial position exists. If we call this derivative of the solution map, or the solution trajectories, give it the name of dx, which is to be understood as the differential of the solutions with respect to the starting point, we also deduce from the limit of this integral equations, or taking the difference quotient of these integral equations, that the differential of the solutions to our stochastic differential equation as a new stochastic process satisfy an ordinary differential equation with random data, namely it is dxt equals 1 plus the time integral which involves the evaluation of the derivative of the B process evaluated along the trajectories of the X process, of the solution process, multiplied with our derivative process. This is the ODE, which defines effectively or characterizes this derivative process. And since we assume that the vector field B, or the coefficient field B, is bounded in C1 norm, we know that there is a constant C which bounds the absolute value of the derivative of that B function, and therefore by Grunwald inequality we can conclude that this derivative process grows no more than exponentially, where C is this exponential growth factor in time. So this means that this derivative process exists and is well defined and is bounded, and we can use this representation of the derivative process, or the existence of this derivative process, to pull the differentiability of the trajectories of the solutions inside the expected value which characterizes the semigroup. So in other words, if we insert this derivative procedure with respect to the starting point into the expected value, which is ultimately the representation of our PT semigroup, we find simply by chain rule that the derivative of the semigroup acting on the smooth function f epsilon with respect to the spatial position, that this exists, and it allows the representation, that's the expectation of the derivative of the f epsilon function evaluated at the position of the solution process multiplied by the value of the derivative process at that time. And so this argument shows two things. It shows first that the derivative of the semigroup with respect to the spatial parameter exists in each point, and it gives also a precise representation of this derivative, which involves the derivative of the f epsilon function and basically the solution of the process and its derivative process. Using this precise representation of the derivative of the semigroup acting on the smooth function at that point, we can also easily conclude that this derivative is a continuous function which also vanishes at infinity. So therefore we have convinced ourselves that the PT operation, when it is acting on a smooth function, it is important here to note that this argument or this representation is true a priori only in case when the function on which the semigroup acts is at least differentiable, because else we would not have any chance to write down this expression. So there is, of course, this is, if you like, another stochastic representation of the derivative of the semigroup, but this is fundamentally different from the one that we are aiming at, because this one here uses the derivative of the function on which the semigroup operates. That's not the formula which we want to do, which we want to obtain. It is an intermediate formula, which for the moment is just guaranteeing that for smooth test function, the semigroup acting on this test function produces a function which is at least differentiable. We can iterate this argument in order to convince ourselves that this PT operation on a smooth function also produces a C2 function. For that aim, we differentiate this solution flow given by the solutions to this stochastic differential equation another time, which means that we differentiate the derivative of the solution process another time. And by a similar argument as before, we find that the derivative process exists, the second derivative process of the solution flow exists, and it is also given as a solution to an ordinary differential equation, which is now slightly more complicated than the one we had before, which involves the first the solution, or the first differential process of our solution process, and of course there is a term which involves the second order solution of the differential process in order to get a true ODE for the second order derivative. So therefore we can state, and here I would also like to point out that this representation is typically true only if we can really talk in a reasonable fashion of the second order derivative of the vector field B. So here we would rely on the fact that the second order derivative of B exists. But in this case, under this assumption, we find that also the operation of the heat semigroup of this, the operation of this semigroup acting on a smooth function, that this yields a function which is even twice continuously differentiable, and that this second order derivative of this operation is again a function which vanishes at infinity. Altogether, this means that we do not only know that this PTF epsilon object, by general theory, is in the domain of the operator, we can say more. We can say that it is actually a function which is C2 smooth, which allows us to use our previously established fact that functions which are C2 smooth and which vanish at infinity, and so that they belong to the domain of the generator, and that the generator on such function has an explicit representation in terms of this second order linear partial differential operator. In particular, we can conclude that this function that we have effectively considered, which is the function in time and space, being mapped onto the operation at time t of the semigroup, acting on this smooth test function f epsilon and evaluated in x, that this function is a C12 smooth solution to this parabolic PDE, which involves the given linear PDE operator curly L. So hence we have now established a connection to the previously established theorem, namely, if we call this function phi of t and x, we have convinced ourselves that this function phi of t of x has the regularity we need for the application of the previous theorem, and that this function phi does in fact solve the PDE, which was the basic assumption for the previous theorem, which was established in the previous lecture. So we can invoke that theorem that we stated at the beginning of our lecture, of this supplementary lecture, and we find that the derivative of this semigroup action on the test function f epsilon evaluated in x has exactly this representation. This is not just straightforward invocation of the previously established Bismuth derivative formula in this particular case, where we note that the function phi naught, of course, phi of not x is of course our f epsilon function. So plugging this particular phi function into the previously established formula yields this formula, and that is almost there where we want to be. There's still this smoothing operation with regards to the epsilons in the formulas, which we would like to get rid of. And that's the last step, of course. Now we send epsilon to 0, and we know that the thing on the right-hand side, of course, has a limit. F is a bounded continuous function, and f epsilon is an approximation of f in supremum norm. So therefore the right-hand side has a limit. It is this limit, and it shows us, since this is an approximation by a uniform topology, and the left-hand side is an approximation by differentiable functions, we also see that the actual function which is approximated is also differentiable, and the formula for the derivative is preserved. So that's just by the usual analysis 1, if you like, result that if you have a function which is convergent, which is approximated by differentiable functions in uniform topology, and if the differentials of that approximating functions converge pointwise, then the limiting function is differentiable, and the solution or the representation of this pointwise representations is also correct. So therefore we ultimately end up at the desired Bismuth derivative formula, which is the formula for the case, if you like, when epsilon is sent to 0. This is exactly the claim, and this representation will also yield with the typical argument that this function, as a function in x, is continuous and vanishes at infinity, where we again make use of the fact that f vanishes at infinity, and we use the fact that the q trajectories or the solutions of this ODE are controllable. So therefore we get that this is again a function which vanishes at infinity, and by subordination, or by taking the Laplace transform of this smoothness statement with regards to the time parameter, we also obtain that for any positive resolvent coefficient or resolvent parameter, the corresponding resolvent acting on the function f produces a function which is C1 smooth and vanishes at infinity. So that's where we are, and this establishes the first order Bismuth derivative formula in case when the coefficient vector field B is C2 smooth. Now, as a final remark to this, I would like to mention that that the result is also true when we do not assume that the function B is C2 smooth, but C1 smoothness is sufficient. Well, why is that true? Well, you could do a similar argument for the semigroup which is established by a smooth vector field when you replace the B by B epsilon. In this case, you would get a slightly different semigroup because it would be governed by a vector field which is a smooth perturbation of the B vector field that has all the smoothness that you would want. And then it's a not too complicated exercise to convince yourself that these expressions also converge with respect to the epsilon parameter, which accounts for the regularization of the B vector field, and therefore you will be able to recover or to produce that corresponding result also in case when B is only C one smooth. And in fact, it goes so the correctness of this formula goes way beyond this assumption. So this is still a too restrictive assumption for certain cases, and if you like, that's a matter of a little bit of research over the last couple of years to what extreme cases you can carry this identity, but that will be not a matter of our lecture in this semester. So this concludes the supplement to the previous lecture, which was dedicated to the first order Bismuth derivative formula for the semigroup induced from solutions to stochastic differential equations. And the next segment will be dedicated to proving a corresponding formula, but now for the second order derivative.